Having started to look at water movement in the form of currents, we will now take a look at waves in the oceans. Here we go. And make sure we've got these settings right here. Now, hello, program. There we go. Not sure how well things work, but at least if you run the PowerPoint yourself, clicking here, you'll get some appropriate sound effects for ocean waves. Our textbook defines waves as the undulatory motion of a water surface. Well, not all waves are the undulatory motion of a water surface, but the ones that we're interested in for oceanography. Well, waves in the atmosphere and even waves that travel through the earth have some relevance as well, but mostly focused on the water ones. To talk about waves, we need to have some terminology. The wave crest is the top part of a wave. The wave trough is the bottom part. And given those, we can measure a wave height from the crest to the trough, up and down. Wave length from one crest to the next, or one trough to the next. Wave period is the amount of time that it takes for a full wave from one crest to the next, or one trough to the next, to go past. So for example, if you're watching waves, maybe going past a pier or something else like that, that's a fixed object in the water, and you know, okay, there's one wave, and there's next wave, and that took, let's see, 2 seconds, then the period would be 2 seconds. A couple more terms here. The amplitude, for different types of waves, there are actually different definitions, so it gets a little messy. But for our ocean waves, amplitude is 1/2 of the wave height. Frequency is the number of waves per time. So that will be the inverse of the period. Instead of how many seconds it takes for a wave to go by, frequency could be how many waves per second. For example, that wave having a period of 2 seconds means for each 1 second, half a wave goes past. So our frequency would be 1/2 wave per second, which turns out to be the unit hertz if you want that technical information. Okay, amplitude, why would we bother having a number that's simply half the height? Well, when you're seeing a water surface, it's a little easier to see how much goes up than how much goes down. So amplitude can be useful in that regard. Again, with different types of waves, there are different types of amplitudes that have their relevance as well. There are lots of different ways that we can classify types of waves. One very important one is based on the wave period, how much time it takes for one wave to go past. And based on that, we can group things into a number of categories, from capillary waves all the way up through the tides. Tides having the longest period, capillary waves the shortest. Capillary waves There, well, having a little trouble. There's starting to see some capillary waves in the water bottle. Well, when zoom doesn't make it disappear. Chop, relatively standard small, short period waves. Swell are somewhat longer period waves that can travel quite far in the ocean. Chop is generally pretty local waves there. Seiches, all those up through that size tend to be generated primarily by winds. Tsunamis are relatively long period waves, often quite large, and they are triggered by some sort of severe disturbance to the ocean. Occasionally it can be a storm. More often it's an earthquake. Various things, we'll look at those more. Tides being quite different, generated by the gravity of the sun and the moon, have a lot of their own special properties. So we'll have a whole chapter dedicated to those, but they are a special category of wave. As with currents, most waves on the ocean surface are caused by the winds. Wind speed, not surprisingly, a stronger wind will tend to give you bigger waves than just a gentle breeze. But also wind duration. Maybe can blow hard, but just one is not going to be enough to build waves up very much. A wind that lasts longer is going to give us a longer, potentially a bigger wave. And also the fetch. This is the distance that the wind is blowing on in order to make these waves. Another factor is, how does the ocean start off? Is it fairly smooth, or is it already somewhat rough from other waves? Well, if the wind's blowing across this and it's very smooth, that wind can just go right on over our surface and not stir it up very much. If there are already waves, the wind is blowing on that, the wind's going to be running into those existing waves more and transfer more energy, and it'll be easier for that wind to get waves built up if it's already got some waves to start with. One other thing that we'll run into as we get into the seiches is if we have an enclosed water body, then the shape of it can be a factor if we set up regular oscillations in the water. Again, faster wind, we tend to get bigger waves, a longer wave length, a greater wave height, and not surprisingly, bigger waves for water tend to take longer to go past, so they'll have a longer period. But again, if the wind's fast but doesn't last very long, or doesn't blow on very much surface, then that's not going to get very far in making waves. A little bit more on fetch, being a less familiar term. If we have a strong wind blowing across something like a bathtub versus a larger pond, well, no surprise, we've got more distance for that wind to blow, and we can build up some bigger waves with the pond. Even if we have the same shape, but in one case the wind is blowing along the length, one case the wind is blowing across the narrow direction, the wind's blowing a longer distance, can make bigger waves in this one with the longer fetch. Once we have those waves, they can travel quite far. This is a picture of a surfer having a little bit of trouble with a big wave off the coast of California that traveled there all the way from a large storm near New Zealand. So the big storm all the way across the Pacific is what got those waves going, and they were able to travel across the ocean to make things interesting for Californians. Given how fast the wind is blowing and a certain fetch distance, that will usually make waves up to a certain size. If the waves do reach that size, well, again, that's not just the wind has been blowing long enough to build up those waves. One common way of reporting how big our waves are, significant wave height, is calculating what's the average of the biggest 1/3 of the waves. Okay, what good is that? Well, bigger waves can be more of a problem, so focusing in on the somewhat bigger ones, but not any weird exceptions. It's kind of a typical big wave in a situation. This is quite handy if you're wanting to know how much damage can that wave do. For example, if a storm is producing significant wave height of 3 meters, and your beach house is 1 meter above sea level, that's not a good combination. Those waves are high enough to be doing some damage to that beach house. Or if you're going out boating, checking the waves, coastal areas, there's often a wave forecast you can use to try to figure out, is this a good idea or not? Of course, it depends on the boat. If we have a significant wave height of, say, 2 meters, aircraft carrier is not going to really notice that much, but you might not really want to be out there in a 2-meter long canoe. If the waves are as big as your boat, that's probably not such a good thing. Depends on the boat and how wet you want to get, but it's useful information for that sort of thing. Ocean waves are progressive waves, a style of wave that is moving across the surface. And what is moving is the wave itself and associated energy. So the shape of the wave that's moving along, the energy with it travels, but the water itself is not going all across the ocean with the wave. Now, of course, the waters go up and down as the wave goes past, but it's not traveling much sideways along with the wave. Now, this is similar to a familiar pattern of making a wave in a rope, as the picture there illustrates. Pieces of the rope are not going back and forth along it. They're just wiggling up and down, but the wave goes back and forth. Another example for the progressive wave that may be familiar is if you've been in a stadium. For the audience to do the wave, it's not one person jumping up and down, going all around the stadium. Instead, folks in each part wave up and down, and the wave travels around the stadium, not the individual spectators. And maybe with distancing, they would travel around. Normally they don't. So here's a picture. We can see some waves coming in. Now, right as they get to the shore, there is some more back and forth motion with the waves. But floating a little further out, which you may have experienced in the ocean if you've been swimming, floating there, wave comes along, you kind of bob up and down, rather than watching ashore. As the wave goes past, water is going in loops, in orbital pattern. Of course, going in circles doesn't really get you anywhere. So the water is basically just going right back where it started. Bigger wave, bigger loop. And then we get a loop going at the surface that sets up water moving underneath. So we get a series of loops, but they're getting smaller and smaller until once we get deep enough, we don't feel any movement of water from the wave, assuming that the area of our ocean is deep enough to allow that. If it's not a perfect loop, then we do have some movement of water. Yeah, if you've been at the beach, you've seen waves wash up onto the shore. Obviously, that water is moving forward to get up onto the beach. So the depth to where we can detect the water moving in those loops is known as wave base. If the water is deeper than that, then the water is going basically just a circle. The wave and the bottom of the ocean are not interacting with each other. Wave running into the sea floor, that's a lot more friction than just moving over other water. So if the bottom of the ocean is deeper than wave base, down there it's calm. We're not stirring up the sediment, and things aren't getting sloshed around as each wave goes past. But if the water is shallower than wave base, then that water is trying to do its loops and it's running into the bottom of the ocean or lake or pond or whatever, water bottle. So instead of circles, things are going to be stretched out more into ellipses and flatter as we go down until at the bottom the water is basically going back and forth. Water going back and forth right by the bottom, this is going to wash things around, stir stuff up a lot more, wash away any small pieces. Using this, we can make a classification of waves. Yet another one. Deep water waves in this definition are ones where the depth of the water is deeper than 1/2 of a wavelength. And in this case, the wave is going along and those loops of water movement do not reach the bottom. So the bottom doesn't affect this wave. Intermediate ones have a depth between 1/2 and 1/20 of the wavelength. There, the loops, they're starting to run into the bottom. The wave is feeling. That's not a technical term, but it kind of describes the wave is interacting with the bottom somewhat. And a shallow water wave, when the depth is less than 1/20 of the wavelength, so wavelength is a lot more than how deep our water is, then that wave is going to interact a lot with the bottom in very major impacts. Again, this is relative water depth compared to the size of our wave. Those little tiny capillary waves I'm making in my water bottle, even though the water in my water bottle is quite shallow compared to a teeny tiny wave, it may be relatively deep. Or conversely, a very, 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 very big wave out in the middle of the ocean may be so big that compared to it, all the way down to the bottom of the deepest trench is not that big. This happens for tsunamis and tides. So again, when we're talking about deep water, intermediate water, shallow water waves, the key thing is how deep is the water compared to how big wave is, specifically its wavelength. Picture highlighting that. Okay, on the left we have a wave that is in water, much deeper than our wavelength. So that's a deep water wave. On the right, compared to the wavelength, that water is shallow. But that doesn't tell us what the overall scale is. We can make deep water waves in teacups by making teeny tiny waves, or we can make shallow water waves in a vast ocean. Another important aspect of waves is how fast they are going, and the term for this is celerity, not celery. Why do we call it celerity rather than just speed? That's to emphasize again that it is the wave that is the speed we're looking at, not how fast the water that's just doing its little loops. We want to know how fast the wave is going, and the term celerity emphasizes that. Celerity and patterns related to it help explain different patterns of waves that you can see. In some places, we see all sorts of different waves all jumbled up together in a relatively chaotic pattern. And these are referred to as seas. Yeah, we just had a definition of seas as relatively enclosed areas of the ocean with significant influence from the surrounding land. And here we have a type of wave condition called seas. Yeah, okay. Come on, sailors. Don't you have a few more words in your vocabulary? Wait, not those words. Okay, so I will try to make a point of specifying what type of seas I'm talking about if I ask you something about them. But usually when you go to the ocean, it does not look like this mess here. Instead, we have relatively regular looking waves of pretty similar sizes. And this condition is known as swell. Okay. Why do we have those two? We'll look at those here. Another special type of wave that we can get, excuse me, could be associated with seas or swell, is breakers. This is where a wave is getting into shallow water and is starting to spill over in some fashion and lose its energy against the shore. These different waves have different effects on people. Fairly large but regular swell becoming breakers is what surfers are looking for. Irregular waves, like in seas, that tends to be just the thing for getting seasick. Although Bloodgood Cutter's poetry is so bad you can get sick just by reading it. Okay, so what's going on? Right in the fetch area, and this is where wind is blowing on the water, making our waves. And some waves start to build up a little more, some are just starting a little later. So we're going to have lots of different size waves together, like in the picture here. and they're growing, getting taller and longer over time. And if we add all this up, then those different waves together will give us some messy, ugly looking mess. That's our typical pattern of waves in sea conditions for waves. So here's that picture again, the seas, and you may know something about the weather. Looks pretty stormy. Oh yeah, storms can have strong winds, and those can be stirring up, building waves, and giving us lots of different waves, and they're all jumbled up all together, very irregular. That's how we make waves. How do we then get waves that are swells, much more uniform in pattern? Now, one thing that's going on, mentioned about the waves adding up, this is known as wave interference. Waves can pass through each other, and the heights will add and subtract. This can be constructive, adding, two waves line up, and so things get higher highs and deeper lows, or they may be going opposite ways, and so they cancel each other out. So we have constructive and destructive wave interference. Usually waves aren't particularly neatly lined up, and so you get complex interference where there's some constructive, some destructive, all piled up together there. This is familiar. You have a couple of drops in otherwise still water. You see the ripples interacting. Sometimes this can lead to a variety of interesting looking patterns. See if the internet likes us on this or not. Yeah, it seems to be getting somewhere. Hopefully it's not running into interference. Well, or maybe not. Oh, there it appears. Okay, so this is a photographer who's made a point of taking pictures as stormy waves are interfering with each other in winter on Lake Erie. And you get some impressive, fun shapes there. You see two different waves running into each other in different directions. Okay. Turns out that celerity, at least in deeper water, is proportional to the wave length. So longer waves, or water waves in deep water, not all waves, travel faster than short waves. And so as we move out from the fetch area, different size waves with different speeds spread out, and we get that pattern of more regular swell because waves of similar speed will be together. And similar speed goes along with similar size. And this pattern, we can imagine a similar sort of thing. Say if we have a race, the whole class, 3 laps around campus. Okay, well, at the starting line, we'll all be together, but won't take too long before some folks are definitely going to be out in front, being faster. Some medium, some of us probably on towards the back, And the longer this goes on, the more spread out will be by faster in the front and slower on towards the back. Same sort of thing happens with our ocean waves. As they spread out from the jumbled sea, the fetch area where they formed, the longer, faster waves will be more and more out in front, the smaller, slower waves more behind. And so further out, we'll see all similar sized waves together. So as we have time and distance, we go from the jumbled up seas to more regular swell conditions. Waves getting into shallow water. We know that affects those loops of the water motion. And no surprise, this affects speed as well. Shallower water, there's going to be much more friction of that wave interacting with the seafloor rather than just going over other water. And friction slows things down. So our wave speed will decrease. And that tends to squish our wave because the front end of the wave is in the shallowest water typically. So it's slowed down more, back's catching up some. So our speed's decreasing, the length is decreasing. Okay, if we squinch our wave this way, water's got to go somewhere. And so waves get taller as they move into shallow water. But you're probably aware, water is not a great thing to try to make a hill out of, unless you freeze it first. So if a wave gets too high, which eventually, as they reach the shore, almost all of them do, then it will become unstable and start to break or spill. So we can recognize different zones as that wave is coming in, more and more affected by the bottom, heights getting taller, lengths getting smaller, the celerity, the wave speed is decreasing. So as waves are coming in, and again, got audio here that I don't think works too well with Zoom. The bottom, the trough, becomes more flat, crests get higher, slows down, wave length decreases, wave becomes, rather than fairly symmetrical, much more asymmetric. Turns out the period stays the same in all this. It doesn't change. If you look for it, you see this quite readily at the beach. We're seeing waves from about where the pelicans are floating, starting to get taller and less wave length. Measure here, if we look at wave height divided by wave length, that's how steep the wave is. As the wave's moving to shallow water, the height's going up, the length is decreasing. So if we make the numerator bigger and the denominator smaller, we're getting a bigger number. So our wave is getting steeper. Turns out that for water on Earth, a height to length ratio of 1/7 is about as much as you can get in a wave before it's going to start to break. Depending on our wave, we can get different styles of breaking waves. If we have a relatively flat bottom to the ocean coming in, it's only sloping very gradually, as is typically the case on our coast here along the east side of the US. Then as the wave comes in, it's going to gradually be encountering the bottom more and more. And so it gradually reaches the point of being too steep, and then the wave starts to spill down the front. So that is our spilling breaker. If the bottom slopes in somewhat more steeply, the wave is encountering the seafloor somewhat more suddenly, and so it can build up height while it hasn't slowed down quite as much. And that can lead to the top not just spilling out the front, but actually plunging out in front of the main wave. This produces what's often referred to as a pipeline shape. And this is what you're really after if you're wanting surfing. That pipeline shape is what's referred to by folks like, say, the Ninja Turtles, totally tubular. They're referring to surfing slang, it being really cool and awesome and like that. If we have relatively steep bottom of the ocean as it comes in, the wave may have very little interaction with the bottom until all of a sudden it's crashing into the shore. That's surging breakers. We don't have significant breaking taking place until it actually is hitting the land. Spilling, that's a lot of energy that's being used up as that water tumbles down the front. So when it finally actually does reach the beach, there's less energy. Surging, that's basically crashing smack into the coast. That's going to give the hardest hit there. Now, this also depends on our wave size as to the pattern. Under stormy conditions, bigger waves, that can potentially have a greater chance of creating a plunging breaker, or at least larger wave coming in. That's part of why you tend to have, whenever there's a storm approaching our coast, you have, besides the Weather Channel folks, crazy surfers trying to go out to the coast and say, hey, the waves are bigger, better for surfing than usual. Well, that's true, but they're also rather more dangerous than usual, and things are likely to get worse. So the emergency personnel are not too happy about the surfers trying to get out there. Of course, different plate tectonic settings will give us deeper or flatter coastal areas. So this ties into that as well. Yep, there are plungers for our plunging breaker. Waves can also bend, and this bending is known as refraction. Ocean waves will tend to bend into areas where the wave is traveling more slowly. Not surprising, if you think of it. Here's the wave coming in. Well, if zoom doesn't make it all disappear. And let's say the middle slows down. Well, then the sides getting ahead will tend to come together somewhat as well. Waves travel more slowly in shallower areas. So if there's a shallow place sticking out, like in the picture here, that place tends to get waves concentrated on it, more wave pounding there. An area that's deeper, further along, like in the middle of the picture, the waves tend to spread out there, be more gentle. So long term, the pattern here is going to tend to erode this more irregular coast into a relatively straight, flatter pattern. Closer view of the picture just to zoom in again. As that wave gets shallow here, that part's slowing down, parts either side are still going somewhat faster, and that leads to them bending in or here, deeper, a little shallower to the side, so the deeper area, the waves spread out more. Here you can see some wave refraction happening. The waves further out, you can see are a little more diagonal, but the close end of that wave is slowing down more, deeper coming in a little faster. And so as it gets closer, it's bending, kind of swinging around to become more parallel as it washes up onto the shore. So again, waves coming in shallow water. You see getting steeper from near the Pelican to closer in. All the way up here, this one is actually breaking. And then the one in front is largely broken already. Of course, that's not the word you use, but it has been breaking for quite a bit. There's still some going on, but it's lost a lot of its energy. It's not nearly as big and tall as the equivalent wave further out is. Here's another good example of a breaking wave, famous Japanese painting, Hokusai. Of course, also this particular version has a few details that were added more recently by someone online. Some additional special types of waves. Storm surge. We mentioned this a bit with looking at hurricanes. This is an effective rise in the sea level in an area. This results in part from the low atmospheric pressure associated with storms. Again, we noted in the hurricane lab that hurricanes, and for that matter, basically all types of stormy weather, are associated with lower pressure. If the air is pushing down less, then the water can push up more. Also, as a storm is blowing along, if it's headed towards land, it's also, with those winds, blowing water in front of it, pushing that extra water on towards the land. And so the combination of lower pressure and water being blown ahead by the winds leads to extra water at the shoreline. With the water being deeper, well then, waves are deep water further along. They bring their energy further in. Also bring to mind storm surge. While it's in a storm, storms also have wind, which makes waves on top of that storm surge. And of course, while this is going on, moon's way up there, doesn't care what's happening down on the Earth, it just keeps on orbiting. And so if the storm surge and the waves from the storm on top of that storm surge happen to be at high tide, then the total water height is even worse. Conversely, if that storm surge comes along, it's right at low tide, then the effect can be much smaller. So here's a picture version. If that's our normal water pattern, the storm surge raises the water level. Also, we've got bigger waves in the wind. When we put those together and at high tide, this not only wasn't such a good time to leave the umbrella and chair out, it might not be such a good idea to still be in that beach house. Storm surge is a major part of the danger and damage associated with hurricanes. I have two pictures here. On the right We have a couple of ships that were washed ashore by Hurricane Camille, one of the strongest hurricanes to hit the Gulf Coast up there with Katrina and Laura this year as well. On the left is a picture from the 1900 Galveston hurricane. The damage from the storm surge there. Galveston is an island near Houston, Texas. And being an island, there's a limit to where you can go if the storm comes in. 1900, we don't have great weather forecasting. We don't have planes. We don't have satellites, anything like that to see what's out in the ocean. Even rather more recently, my mother-in-law could remember as a girl growing up in South Florida that your hurricane alert was if suddenly all the birds leave the beach, that's not good. You got about half an hour to get ready. So Galveston, a lot of people living on this island and not a whole lot of warning. And major hurricane came in and storm surge completely flooded the island. Several thousand people killed. That's actually the worst natural disaster that we've had in the US in terms of number of deaths. Big storms can make big waves. The tallest waves that we've measured that were not tsunamis were very large waves associated with hurricanes. Not rogue waves, which we'll look at a little bit later. NOAA has a video on storm surge. We looked at it a bit earlier in the class, but again, I'll have the link that you can go to watch that Oceans Today series. They've got a number of videos, including on storm surge. Another special type of wave is the seiche or standing wave. This is basically a water surface that is doing kind of that sort of thing, a seesaw back and forth pattern. The node is the term for the point where, as the two sides are doing this, I'm not managing it perfectly well, but basically somewhere right on my nose is where things going up and down, that bit of water is not going up and down. Antinodes are at the ends where things go up and down the most. And typically that will be at the edges of our water basin. And typically we are at the edges. We live on the land, so we're going to tend to be at the edge of a basin rather than hanging out somewhere in the middle unless we're on a boat. And so we have, with the waves, depending on the shape of our basin, a standard pattern, an enclosed basin. The node can be in the middle, open at one end. The node is at the end, antinode towards the inside. This pattern of nodes and antinodes we also encounter with sound waves. This is part of the way that musical instruments work. For example, a wind or horn instrument, you're opening and closing different valves, and these create an overall tube of various lengths, which add up to allow certain types of sound waves to be strengthened and others to cancel out. And so you get a particular note out of, say, your flute or trumpet or whatever it may be. Similarly, for a string instrument, as you hold down the string, the vibration back and forth, the length there will be a node at either end of the string. and that determines what note you've got there. Different shapes, we get different patterns in our standing waves. um, a strong storm, let's say things right here, can potentially produce waves that set up the SACE type pattern. I've got a link to a video there of that happening. And what especially sets up just the right things for SACE is if we have some sort of pattern of waves coming in that matches just what the pattern is generated by the shape of our area. So a similar pattern goes along with, say, pushing somebody on a swing. If you just kind of aren't paying attention, push, 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 kid on the swing's probably not real happy with you. Not really doing anything regular there. But if you're paying attention and just as that swing comes back, you give it another push, comes back, give it another push. Your push is timed to reinforce that wave. And pretty soon the swing is going back and forth farther and farther. So we can have that same thing happening with our ocean waves. If the incoming wave comes along at just the right time to match the previous one bouncing back, then they reinforce and we build up stronger waves, and essentially our body of water is sloshing back and forth in the SACE. Different shapes give us different patterns. For example, this can be used to splash lots of water out of a bathtub without making loud splashing. Obviously, if you jump in the tub, it splashes all over. But if you were to just kind of give the water a push, as it comes back, give it a bigger push, and keep on doing that, eventually you build up bigger waves to splash out, which probably isn't what you want for your floor, but if you did want to splash it out, that would work. Another special type of wave is the internal wave. As the name suggests, this is not on the very top of the water. It's on top of a layer within the water. So, for example, on top of the picnic line or other layers in the water. Now, we do it. Wave steepness. If the wave gets a height above 1/7 the wave length, then that doesn't hold up so well. But that's because our water is surrounded by air, which doesn't hold up water very well. Those internal waves are surrounded by other water. So it's going to be much harder for that wave to spill. And so the numbers when our internal waves are different. They tend to travel more slowly, but can be very, very big. But they are waves. They can bounce off something, reflect. They can bend or refract. Different ones can add and subtract, so we have wave interference. Although they can get a lot steeper, eventually, if it gets steep enough, internal waves can break as well. So we get all these different things happening with internal waves, much harder to see because they're water under other water, but it happens. What makes a wave down there? The wind doesn't blow on, obviously, but tides, with those being great big waves, those affect the layers down there. Currents, two different currents trying to flow past each other, that's going to stir things up. Big enough storms may be able to stir things up, going down deep enough to hit different layers. Or if there's, say, an earthquake or underwater landslide, things like that happening. Those could be additional ways of stirring things up and creating internal waves. Picture here illustrates some internal waves that were detectable because there was there were a couple of distinct layers of plankton in this area. And enough that sound waves bounced off, made an echo, and we see waves in those layers corresponding to waves of water layers that the plankton are concentrated at the boundaries of. Another special type of wave is the tsunami. An older name used for tsunamis was tidal wave because it was as if the tide came in when it wasn't supposed to. But since it isn't really the tide, that name has been largely abandoned as potentially confusing, and instead the word tsunami is used. Tsunami is a Japanese word meaning harbor wave. Normally, if you're in the harbor, you're relatively sheltered from waves out in the open ocean, and things are pretty calm. But from time to time, folks in Japan notice that you get this really big wave and actually gets quite big in harbor, sometimes extra big there. So they had a special name for it, and that's now in general use in English as well. You may recall way back from around the beginning of this that a tsunami is a relatively long period wave. It takes a long time for a tsunami to go past a particular point because it is also very long in its wavelength. Longer wavelength typically goes along with faster speed, although there are complications depending on is this deep water, intermediate, or shallow water, again, compared to our wave size. 760 kilometers per hour. You have been that fast, perhaps, if you have ridden in a jet plane, but not in a car, definitely not by foot. So quite fast, and they are very long waves, and so that's typically a lot of water. Long wavelength, shallow to intermediate waves, even in the deep ocean. Again, it's relative to our wavelength. Now, out in the deep ocean, great big long, but there's plenty of room to spread out, and so the wave height is quite small. If you were out on a boat, you wouldn't notice it because of all the other smaller waves on top of it. But when that great big wave gets into coastal areas, again, the wave length decreases and the height increases. And when you have a huge wave, if you pile enough of that up, you can get an extreme high wave. Not all tsunamis are big. You can get tsunamis that are that big, but you can get ones that are a lot bigger as well. Major disruption of the water are in various ways how you make tsunamis. Earthquakes are the most common. Volcanoes, either if the volcano is in the water, that can potentially be a ready way of making a tsunami. If you have an island, all of a sudden it blows up, isn't there anymore. Well, water's going to be crashing in, making big waves there. Of course, the explosion probably pushes water out the other way. Also, as a big hotspot type volcano builds up, that's a lot of rock piled up. Eventually, it may collapse. And a huge amount of rock crashing into the ocean that can make a tsunami as well. Any other cause of a submarine landslide that could potentially trigger a tsunami, because all the stuff under the ocean is moving, and so the water has to go somewhere in response to that. Uh, Even sometimes just the right conditions in a very large storm can trigger a tsunami type wave. Of course, when a really huge tsunami will just crash an asteroid in the ocean. um, there would have been quite impressive ones with the end of the dinosaurs, for example. But it also has to be the right arrangement to make a tsunami. Earthquakes, of course, we noted different types of faults back when talking about plate tectonics. And if we have a transform fault situation, one side slides past the other, yeah, that's making earthquake waves, but things sliding around in the bottom of the ocean, that's not nearly that disruptive. However, if we have a large earthquake that suddenly either, get the water bottle shown up here, suddenly either drops part of the seafloor down or moves it up, if I didn't have the lid on the bottle, those would not have been good. A vertical movement of the seafloor from earthquakes is typically what really makes for big tsunamis, if it's a big earthquake. Now, there are potential exceptions. After all, an earthquake is a pretty good way of causing a landslide. So there are some exceptions, but typically, whenever there's a large earthquake near or under the ocean, there's an alert of potential tsunami sent out. And if measurement shows that the earthquake moved the bottom of the ocean up or down, then that's definitely of greater concern. If it's just sideways, typically that's better. Although we seem to have had primarily sideways with tsunami a few years back in Indonesia. Exactly what happened, whether not all the earthquake motion was sideways, but it had some up and down going on as well, or did it trigger an undersea landslide? We're not entirely sure yet on that one. No surprise, really big earthquake can potentially trigger a worse tsunami. Tsunamis traveling quickly. Here's an example. Earthquake was off the coast of South America, and in just over 19 hours, it's starting to run into Japan. So yeah, that's about as good as you could do with an airplane. So rapid notification is important. And so having early warning system in place is a key aspect of protection from tsunamis. That huge one hitting the Indian Ocean just after Christmas 2004. One reason why it was so devastating is that the Indian Ocean historically hasn't had quite so many tsunamis as Pacific, and so there wasn't much of an early warning system in place. Here's a picture of the tsunami waves coming in. Devastation from the 2004 Indian Ocean tsunami. One reason that tsunami waves can get so big, again, waves are slowed down as they get in shallow water. Tsunamis do not consist of just one wave. Typically, there are multiple waves, and so you need to pay attention on this. First wave coming in, it's slowed down. Next wave is still going faster. It can catch up and add up. Wave interference, constructive, producing a net result of a noticeably bigger wave. Also, you can just have variation in the sizes of tsunami waves. And so that's important to keep in mind. If there's a tsunami alert, you need to head for your shelter and stay there until you have confirmation things are safe again. It was vividly demonstrated by a tsunami that I think the actual earthquake was up in the Aleutians, Alaska, but the waves hit Hawaii. And so we did have a tsunami alert, and people headed uphill, and a big wave came along, and then people went out to see what had happened from that, and an even bigger wave came along. Definitely need to stay sheltered until we've got confirmation that it is safe to go back. Another special type of wave is a rogue wave. This is a wave produced by wave interference that is much bigger than expected for conditions. Again, we mentioned for a certain amount of wind and fetch area, there's a certain typical height of wave you expect out of that. Just from those, you can predict your standard wave height, what's your typical pattern. But as it turns out, that typical high wave, if you've got enough interaction between waves in various fashions, you can potentially end up getting a wave much bigger than expected. This was doubted for some time. Was there a really big wave or just a sailor that had too much rum? And of course, also, if you get a wave that's big enough, then you don't have any sailors left to report it. So proving that these exist reflected two key things. One was better mathematical calculation with computers enabled having fewer simplifying assumptions in our calculations of how waves behave. And it turns out that when you get more of the complexity in there, you start to sometimes see the occasional wave much bigger than you would have expected. Another thing is actually being able to detect these, airplanes, satellites, those can detect a big wave without being directly in its path, the way a ship would be. And we've also have increasing number of things that hold still out in or by the ocean. For example, oil platforms or lighthouses. There was a classic example of a lighthouse in a big storm. Afterwards, a large rock was found that had been tossed by a wave over the lighthouse. That's a big wave. And so this led to recognition that rogue waves do exist. The picture here illustrates one situation. If we have a current tending one direction, but the primary waves are coming in an opposing direction, then that current wave running into each other pattern can give extra big waves. A classic area for this is off the west coast of southern Africa, where we have the Agulhas current and waves coming up from Antarctic storms running into each other. Okay, and it is not liking something on the NOAA site there, but we do have some pictures of extra big waves like these interacting with ships. For that matter, people have been able to model these in lab experiments. There's a classic video where experimenting around with the pattern of waves being produced in a wave tank ultimately led to one extra big wave, which was bad news for the Lego pirate boat that they had in their wave tank as an example. Here's a picture where you see this extra tall wave compared to everything around. Now this is stormy seas conditions, so all sorts of different waves there, but here's this extra big one there. Turns out this is quite challenging to model mathematically, but there are potential interactions between waves. As a wave gets big, it has potential to interact with more other waves, and there are multiple things that go on to lead to these extra big waves. Obviously, if it's too big and too sudden, it may just destroy things, and we don't have great information. Computer modeling suggests that a rogue wave out in the open ocean could reach 200 feet or more in height. The highest wave that we have recorded was from a landslide in Alaska. An earthquake triggered a major landslide, and so a bunch of the side of the bay goes crashing down into the bay. And no surprise, it makes a great big wave, a tsunami type wave, and splashing up onto land that reached 17,040 feet. We actually have eyewitness accounts of this. There were some folks in boats there at the time, and now our boat is up above the trees on the wave. This is not good. Let's try to get out of here. In the highest actually measured waves that weren't due to tsunamis were within the expected range, but the expected range was huge because it was in the middle of a hurricane. They weren't actually rogue waves, but potentially a big rogue wave could be quite devastating to a ship. Again, here's an illustration of the bending interference that can happen if we have a current, especially one with variation in its flow, interacting with waves. So to sum up, most ordinary waves are produced by the action of wind on the water. Wind duration, how long the wind is blowing, the wind speed, well, velocity incorporates direction as well as speed, and the fetch, the distance that that wind is blowing on, affect how big a wave we can make from that wind. As a wave travels along, we have those loops of motion. These loops can run into the bottom if we have a shallow water wave, and this will affect our wave celerity, our wavelength, wave height. We have the different patterns of seas, the irregular waves, where we are building the waves in or right near the fetch area, and the pattern of more regular waves of the swell as those waves spread out, and in doing so, sort themselves by speed and wavelength. Further features of waves, we have the potential bending of waves, refraction, the extra high water level in large storms of storm surge, the seiches of that bounce back and reinforce pattern in the waves, internal waves, waves rather than at the ocean surface are at the surface of another layer of water deeper down, tsunamis being a long wavelength wave caused by major disruption to the ocean, well, or other water body. There was quite a sizable tsunami when the eruption of Mount St. Helens crashed into Spirit Lake. Rogue waves, those are extra large waves compared to what's expected for conditions due to complex interference. Again, compared to what's expected. If we only expect our waves to be that big, and we get a wave that big, that would be a rogue wave, even though it's not one we're real worried about. because it is bigger than expected under the conditions. And that finishes waves, apart from that one.